So in this section, we're going to go ahead and talk about this idea of rates of change. Remember, we opened up this course with a large discussion about slope and computing slope and finding equation of a line. Well, average rate of change is the idea that this is going to look at how y changes with respect to x. In fact, rates of change, remember we talked about that slope was nothing what we're going to call later on rates of change. And the definition looks slightly different than what you recall from slope, because slope we have y2 minus y1 over x2 minus x1. Here we just have the function value at a value b minus a function value at a. So these are y values, and we subtract their x values in the same order. So we have function of b minus function of a uses usually our most rightmost value from our leftmost value, and the same with our x's, our leftmost value our rightmost value from our leftmost value. Right? And average speed or velocity is one way to look at average rate of change. Average speed is a change of your distance traveled over the time that you've traveled. So here we want to look at finding an average rate of change for this function here over interval between 1 and 3. And we're going to go ahead and round that to 4 decimal places as necessary. So sometimes you're going to not have nice whole numbers anymore. You're going to have decimals. And because they ask for decimals, you cannot leave this as a fractional answer. All right. So we have y is equal to x squared plus 2x. Okay, so this is a quadratic function. And what you want to do is you want to find the corresponding y values for each x. So we're going to go ahead and plug in 1, and we end up with the value of 3. And when we plug in 3, we get the value of 15. So we want to take our rightmost value of y, 15, subtract it from 3, which is our leftmost value of y. And we're going to do the same thing with the x's. So 15 relates to 3, and the value 3 here, y value relates to 1, and we're going to subtract those values. And in this case, we end up with an average rate of 6. So in this case, it was a nice whole number. All right. And so we're going to do this fairly often, and then from here you are also going to be able to find equations in relation to these average rates. So now we're going to go ahead and look at a different equation. So here we have an exponential equation, y is equal to e to the x. And we want to find the average rate of change between x is negative 2 and x is equal to 0. And again, we're going to go ahead and plug those values in. So at f of negative 2, we just have e to the negative 2. No need at this point to go ahead and get any decimal values. We're just going to go ahead and use this as it is. When we plug in 0, we get e to the 0, which is just 1. So we get a nice whole number, which we can go ahead and use in our equation. So our average rate of change is going to be our function at 0, because 0 is our rightmost number, minus our f of negative 2, which is our leftmost number. And I'm just going to write that as 1 minus e to the negative 2, because I know that I am expected to round this to 4 decimal places at the end as needed. And I'm also going to go ahead and have 0 minus a negative 2. Now here our negative signs are going to become plus. So I have 0 plus 2, which is just going to be 2 on the bottom. And when I go ahead and perform this division, now what I would do in your graphing calculator is make sure you put parentheses around the top and then divide by 2 so you get the appropriate decimal number. And when I go ahead and round this, I have 0.4323. Right, and so now we have this idea of average rate of change, but average rate of change only tells us what the change is between a specific time interval over or whatever, but it doesn't tell us what is actually going on during that time frame. So we don't know if it took us 5 hours to go 30 miles, it doesn't tell us that for a long period of time we may have been stopped. All right. So it doesn't tell us how fast we were going in between that time, how long we were stopped or anything like that. But what we want to know is we want to know what is happening at a specific time or a specific instant. And that's what we really want to go ahead and look at. So the average is not going to tell us what's going on in between unless the A and the B are actually really close to each other. And so now we need to go ahead and define an instantaneous rate of change, because that is what we're interested most of the time within the business area. So let's go ahead and look at it. Our average rate of change graphically is just 2 points on some sort of function, but it doesn't tell us anything that's going on right in this area here. Our instantaneous rate of change is like a line that goes right alongside of our graph at a specific area, and we want to know that specific time frame, what's happening at that point, instead of over a large period of time. All right, so for an instantaneous rate of change to occur, we need 2 points to be really close together in order to really compute it, okay? And then we could go ahead and compute the limit at that point, and we could go ahead and just figure out the slope just like we have been, or rate of change. And it'll give us a good idea of what's going on at that point if A and B are incredibly close together, all right? If they're not close together, we need to use a slightly different formula. All right. And what we're looking at is we're looking at this idea of where A is and another point called A plus H, which we're not identifying here. Okay. And so these 2 points are going to be pretty close together, where H is going to be incredibly small. And we're going to use the same idea of rate of change, but instead of subtracting 2 numbers on the bottom, this small area of H, which is going to be very tiny, is the only thing that's going to be in the denominator. And we're still looking at our Y values of f of A plus this very small number minus the function value of f of A. And this second definition is what we're going to go ahead and use to compute our instantaneous rate of change. So let's look at a problem. So we have a position of an object moving in a straight line is given by t squared plus 5t plus 2. And we're going to go ahead and use that second definition as limit as h approaches 0 of f of A plus h minus f of A divided by h. And A is equal to 1 since t is equal to 1. All right, so we're going to call A t, which is 1. And we're going to go ahead and plug it in. So here we have our instantaneous velocity at s of 1 plus h minus s of 1 over h. Okay, so we need to go ahead and compute s of 1 plus h and s of 1 separately. So we need to go ahead, plug them into our equation. Now, when we have s of 1 plus h, we're going to end up squaring it and go ahead and doing some distribution. All right, and we are going to have h values within our s of 1 plus h, and that's totally to be expected here. So we go ahead and FOIL it out and do our distribution and add 2. We end up with 8 plus 7h plus h squared. All right, and this is going to be our f of A plus h value we're going to plug into our equation. When we go in and plug in f of A, or s of 1, we just go ahead and square 1, add 5 times 1 plus 2, we just get 8. All right, so we're going to go ahead and plug those values into our formula. So we have our polynomial from our f plus 8, our A plus h, and we go ahead and subtract 8 from that. Now notice here that our 8s are going to go ahead and cancel. And what we have is the limit as h approaches 0 of 7h plus h squared divided by h. And what we're looking at now is we're going to go ahead, pull out the h that we can out of the numerator and cancel. And now we can go ahead and just take the limit of 7 plus h. Now as h approaches 0, because it's not undefined in any way, we can go ahead and just plug in 0 for h, and we can find out that our instantaneous velocity is 7 plus 0, or simply just 7. All right, let's go ahead and look at another example. And we're going to look at the position of an object moving in a straight line. And again, we have this lovely quadratic, 5t squared minus 2t minus 7. And we want to find our instantaneous velocity at t is equal to 2, which again implies that our A value is going to go ahead and be 2. So we're going to go ahead and figure out our a plus h and our f of a. So we will go ahead and plug in 2, s of 2 plus h, and that's going to be equal to 5 times 2 plus h squared minus 2 times 2 plus h minus 7. All right, and we're going to go ahead and plug it in. We're going to head and FOIL and distribute, and we end up with 9 plus 18h plus 5h squared. All right, and when we go ahead and plug in 2, we just go ahead and get the value of 9. And so we go ahead and put all that together, and we're going to get our instantaneous velocity. And so we're going to take the limit of our f of a plus h value and minus our f of a, which was 9, divided by h. And again, we're going to go ahead, factor out that h, cancel it out, and we're taking the limit as h approaches 0 of 18 plus 5h. Now remember, our h is going to 0, so we're going to have a 5 times 0, which is just going to leave us our instantaneous velocity of 18.